So last time we studied about the Coulomb's law and how two charges apply forces on each other. What is the amount of force? What is the direction of force? What is the magnitude of force if two charges Q1 and Q2 were separated by a distance? That's what we learned, and we compiled all of those small statements in form of Coulomb's law. This is what we observed. Magnitude of the forces are equal and direction of the forces are in opposite direction. If you increase charge on one particle, forces on both the particle gets increased, and magnitude of forces is equal, opposite in direction. So forces are they are action reaction pair, and the force varies as inverse relation with the distance. That means it follows inverse square law, just like gravitation. Now further ahead, we want to discuss about something called electric field. And for a quite amount of time, it baffled scientists that two charges. How does the second charge Q2 knows about the presence of the first charge? And if we hear about stories about Einstein, even Einstein was baffled by why two magnets attract, why two magnets they repel each other without even touching each other. So it was hypothesized that charge Q1 is releasing something at point A. It has something in this region. It has some effect in this region. Because it doesn't have a mouth, it cannot talk to the second charge. And this something, its effect in this region was given a term named as electric field. So what scientists said that there must be coming something out of the charge Q1 such that other charge can detect its presence. And this whole theoretical concept brought a new insight in this electrostatics. And what they found that this field or this something, this flow is, they called it field. They called it field, and it was related to electrostatics. So they called it electrostatic field or electric field. Now, this electric field at this point, let us say r distance away, this should be independent of charge Q2. And it must be strong as we go near to the charge. So they formulated a formula to give the value of this electric field. And this was given by force applied when you place a test charge Q0, force applied by Q1 on the test charge divided by the test charge. Now I'm calling Q0 as test charge because test charge should not disturb the original charge. They should be really small. The test charge should not disturb the original charge, original force, original field. If I apply the Coulomb's law here, I will get it as Q1 Q0 by 4 pi epsilon naught into r square divided by Q0. From here, I get the electric field, the magnitude of electric field due to a single charge particle, single point charge. And to remember it simply, electric field due to a single particle or single point charge is given by kq upon r square. Easy result to remember. And as you can see from here, the unit can be written. The unit of force is Newton, and unit of charge is Coulomb. So unit of electric field will be Newton per Coulomb. And this is how charges know that there are other charges which are present in the region, and there is force acting on the charge. So before going into the properties of the electric field, we'll first do a few problems. And just as you see, if suppose there are two charges, a very simple problem will take. If there is a charge Q, and there is a charge another here, and the charge here 4Q. And you want to find a point somewhere between these two charges, where if you keep a third charge, the net force is 0. Okay, so you can directly find the point at which electric field is 0. As you see here, electric field is force per unit charge. So force can be written as charge times the electric field in the region. Force on this particular charge will be equal to charge times the electric field. So if suppose I keep my test charge here at this point A, which is, let us say, x distance away from the first charge. So of course it will be r minus x distance from the second charge. In that case, the field at point A, the electric field at point A should be 0. And we can find the point at which we place the third charge, where net force is 0 or where it will stay in equilibrium. So here at this point, Q will be giving electric field in this side. That will be electric field due to Q. And for Q, it will be giving electric field in this side. So what you have to understand from here is that if the direction of force on a positive charge is towards left, then direction of electric field is also towards left. It is just like force, but divided by the value of the charge that you keep here. So yeah, you guessed it right. You can apply principle of superposition for electric field also. And you know that electric field due to 4Q should have magnitude equal to electric field due to Q. So this will be 4Q upon x squared equals to Q upon r minus x squared. To solve this, send easy solution. So 4 is equal to x upon r minus x whole square plus minus 2 equals to x upon r minus x. If you solve this, you'll get a value of x is equal to 2r by 3, or 2r x is equal to 2r by 3. This electric field due to 4Q, here it should be 4Q upon r minus x whole square. And here it should be x square, because this is electric field due to 4Q. So 4 should be equal to r minus x upon x whole square. From here we get r minus x by x is plus minus 2. And if you calculate here, it will give you x is equal to r by 3. So if you place a third charge over here, you will get net field as 0 and net force as 0. So just as force, you can apply the principle of superposition in electric field. And we can derive it from principle of superposition of forces. Suppose you want to find the net electric field at point A. So the
Right.
yeah.
Do we have to note down all this?
I'll be sending you the this whole PDF thing, whole thing as PDF. And if you have doubts, you can raise a hand and ask me questions.
Good evening, sir. This is Nihar Soni speaking,
Yeah.
a student of this batch.